Okay, what are the different types of solids? This is going to be the specific different types of solids that come from bonds. So this would be a ionic, metallic, covalent, network covalent. Make sure you know the difference between those. That will be important. Network covalent, and then atomic. There we go. What types of atoms can undergo network covalent bonding? That is going to be our non-metals. So these are going to be things that can do normal covalent bonding. So normal covalent bonding. They're just going to keep going and going and going, okay? In particular, we're going to see Si, which is silicon, and carbon doing this because they each can make 4 bonds, right? So they have all of this extra room to just keep building and building and building and building and never really stopping, right? When a network covalent substance is melted, what type of bond must be broken? Well, because this is all one giant molecule, then it is a covalent bond. You actually need to break. If I've got diamond or graphite or something, I've got carbon-to-carbon bonds, and I actually need to break that carbon-to-carbon bond. What type of attractions are broken when a covalent solid is melted? Well, that would be either hydrogen or polar bonding, or London dispersion forces. Basically, for this one, because let's draw a little H2O over here. H2O. Because each of these molecules are separate, the only thing holding them together is that intermolecular force. Why is there a line on this? That's weird. Is there a line on your screen? Ugh, this is annoying. I'm trying out a new thing. I don't really like it that much. It's kind of obnoxious. Oh, yep. There we go. Okay, no more line. Okay. So because we've got these guys together, they've got this intermolecular force that's bonding them and keeping them close by each other. When it melts, we're just breaking that intermolecular force. That's the easiest thing to break. The covalent bond is much stronger than that intermolecular force. So that's all we're doing. Okay, so fill in the table below relative to the intermolecular forces indicated in number 4. Type of intermolecular force. Well, we're just going to say polar and hydrogen bonding. Because keep in mind that hydrogen bonding is just a much stronger version of regular polar bonding. It's really the same phenomenon, just when we have these really 3 specific type of bonds. That would be the O to H, the N to H, and the F to H. Okay? All right, and then what's the other type of intermolecular force? It's going to be London dispersions. Whole bunch of London dispersions up in here. Okay, and then factors affecting the strength of that force. What are the factors that affect the strength of a polar or hydrogen bond? Well, that's going to come back to our bonding unit. Remember, we looked at when we have these types of bonds, we really have this polarity going on here. So this is going to be simply the strength of the polarity. Right? Remember, it was that those electronegativities, the differences between them. We had a scale from 0.4 up to 1.8. If our difference fell in that scale, then it was a polar bond. The farther it is along the scale, the stronger that bond is going to be. London dispersion forces, because this is just going to be, like those little positive charges with an electron cloud, just a displaced electron cloud. Because it looks like this, because it's all about that electron cloud moving over, It's going to depend on how big that electron cloud is or how many molecules there are. Okay? So it's size of electron cloud slash number of molecules. So the number of molecules, if there's enough molecules, it'll make even these tiny little London dispersion forces a lot more significant. That's why things like oils have such long carbon chains. The longer that carbon chain, the more it'll stick together. Okay? When a sample of sodium chloride is being melted, what force is being broken? Well, NaCl, remember, an example is right down here. NaCl, each darker one, these are all sodiums, and then the lighter one's a chlorine. There we go, okay? Whenever a substance like this is melted, see these little lines? Those are all the ionic bonds. We're just drawing that really strong attractive force there. If this thing melts, these bonds all break. As a liquid, the only difference is that these sodiums and chlorines, they still hang out near each other. They're just able to move around, right? It's like imagine it's a giant ball pit. It's a ball pit of molecules. So they're all still sitting together near each other, but they're free to move around each other. As a gas, they would all just disperse. They'd all be gone. Vamoose. Okay. So when a sample of NaCl is being melted, what force is being broken? That is the ionic bonds. Okay, what are the factors affecting the strength of an ionic compound? Well, one, that's going to be atomic radius. And here, let's grab a little scrap paper if I can find one. Yeah, that'll do. So, atomic radius, think of it this way. So if I've got a positive charge here, and I've got let's do iodine, which is going to have 5 of these layers. And that's 1, 2, 3, 4. One more. And then let's bond iodine with, well, let's just say lithium, just for the sake of an argument. So lithium. So this is iodine, this is lithium. Lithium only has 2 layers. So lithium iodide, both of them have a 1 for a charge. Well, 1 for a charge, plus, minus, plus 1, minus 1. The difference is that iodine has this massive electron cloud. Look at how big that is. That is so much larger than the lithium cloud. So an electron hanging out right here, if I've got a little electron right here, he's going to be attracted to the lithium nucleus. That's got a little positive charge in there. It's also going to be attracted to that positive nucleus in the iodine. That attraction is really what's going to try and hold these together. Well, because iodine has such a large radius, that electron's not going to feel as attached to the iodine. Now let's compare that with something like lithium fluoride. They're going to have the same charges, same exact charges. The difference is this lithium over here. I really probably should have drawn this on the right side, or the left side, whatever. Doesn't really matter. The fluorine, it's going to have the same number of clouds. So an electron on the lithium is going to feel a much stronger pull. There's going to be a lot less electrons in the way, right? If you remember back to that effective nuclear charge, remember it's really the electrons out here, they're repelled, they're repulsed by these electrons. There's a bunch of electrons hanging out here. This guy's going to be pushed away by these, but attracted to the little protons in the center of the nucleus. So with a smaller shell, there's fewer electrons to get in the way. The larger shell, there's a whole bunch. I mean, look at this. It's like a little army of electrons, you know? There's a lot more electrons trying to push this guy away, right? It's like a guy trying to court a very pretty woman, and she's got all these brothers that are just getting in the way, going, no, you can't talk to her, you can't see her. It's going to be really hard for this electron to, keep being attracted to that proton, that nice pretty proton, because she's got all these brothers in the way. They're all trying to keep him out of the loop. This one, brother, dad, that's it. Hey, and I even got along with one of those. Oh, good, we're in. There we go. Nice and simple. So that's really how the ionic radius is going to affect that. The other thing that's going to affect it is the charge. How strong is that charge? So if we've got a stronger charge, it's going to be less likely to want to break down, right? For a lot of the same reasons. Okay. So then with what you know about the strength of ionic compounds, write out 3 different ionic compounds and list them in order of increasing melting points. So for this one, we could think of 3 different ionic compounds that are going to have differing radiuses or differing charges. So the first answer key I did differing radiuses. So I had NaF, NaCl, and NaBr. And if we look at a periodic table, we'll see that going down this way, these are all in the same group. The only difference is, really going to be their atomic radius. They're not going to have a different charge. Each of these has a -1 charge. The difference is bromine is going to be larger. It's going to have a bigger electron cloud than chlorine, which is going to have a bigger electron cloud than fluorine. So the actual the melting points is going to decrease going this way because this sodium is going to be less attracted to bromine than it is to chlorine and less than it is to fluorine. Okay? So that's how the ionic radius could affect it. But what about the charge? How about this? Well, I could have a NaF. Well, this is going to have a lower melting point than something like Na2O, and that's because fluorine has a -1 while oxygen has a -2. And that's still going to be a lower melting point than something like Na3N, because that nitrogen is going to have a -3 charge. So the bigger charge, the stronger it's going to pull in. Think of it like having a stronger magnet. It's going to want to pull harder. It's going to be harder to pull those magnets apart. Think of the super strong magnet I have on my door. It's harder to pull that off than just a standard bar magnet. These are going to have the same phenomenon. It's going to be harder to pull them apart because they have a stronger charge. Okay? What is the fundamental difference between ionic and molecular substances when melting? Well, the big difference is ionic breaks ionic bonds. Covalent, and this is specifically covalent. This is not network covalent. This is regular covalent. So that's going to be, like these water molecules getting together. The only thing holding them together is that intermolecular force. So covalent breaks an IMF, an intermolecular force. Okay, and that is going to be a lot weaker. I can try and find. I'll try and find that later. But there's a really nice handy chart that shows just the magnitude of differences here. And I think it's on the order of. I think a regular intermolecular force is going to be something like 10 to 40. I want to say newtons for the force, and an ionic bond is going to be in the thousands. It's going to be in the thousands of newtons. So I don't think Newton is the right unit of measure here, but regardless, you can see the numbers are a lot larger. The numbers are going to be substantially higher. Okay. And what type of substance is at the right? This guy right here. So this is a 2-carbon chain. That would be F. If you remember our organic naming from the very beginning of the year, I'm sure you don't. But then it's got that OH group at the end. That means it's an alcohol, so ethanol. Ethanol is a covalent solid. It is covalent because we've got these covalent bonds right here. That's what these guys are. It is not a network because we can see it stops. Look at this. The hydrogen, it stops there. The hydrogen isn't able to bond out to anything else. It's not able to do that. hydrogen can only have one bond. So really that carbon, that oxygen, those could bond to something else. In fact, we often see things like plastics is carbons, oxygens, nitrogens, that kind of thing. Those all bonded together, making this covalent network solid. But in something just like this, ethanol, I mean, I've got a vat of this stuff in the chemical room. It's really just these individual molecules all hanging out together. So what are the factors affecting its melting point? Well, that's going to be the polarity of this. And look, we've got this oxygen to hydrogen bond here. Look at that. That's going to fall under the category of hydrogen bonding. So hydrogen bonding is going to be the biggest factor affecting its melting point. That's also going to affect its boiling point. So ethanol, the alcohol version, which has that OH group over here. Oh, nuts! You guys probably couldn't see any of that when I was doing it. Okay, let's cover it again. Okay, these little circles, those are the covalent bonds. This little circle is noticing the oxygen to hydrogen. That's both the alcohol as well as providing a hydrogen bond. Okay, so now you can see it. Great. I'll try to be a little more intentional about that. So, ethanol, the alcohol version, is at this temperature, the stuff that I have in the back room, is a liquid. Where ethane, which would just be, if I just get rid of this oxygen, and I had carbon to carbon, and just had hydrogens, no oxygens, well, see, I don't have that oxygen to hydrogen bond anymore. I don't have any polarity in this at all. The only thing that would keep ethane together would be London dispersion forces, which are very weak. So at room temperature, this is a liquid, this is a gas. And they have a very significant difference in their melting and boiling points because of those intermolecular forces. Just a small difference, like adding oxygen, drastically changes those properties. All right. What type of substance is at the right? Covalent network, or ionic? Well, this is sodium chloride. This is going to be ionic. Of course, we should know that. NaCl. Great. What are the factors affecting its melting point? Well, the melting point in an ionic compound is going to be affected by the atomic radius, just like we looked at above. Right? Just like we looked at right here. It's going to be the atomic radius and the overall charge. Great. And then we're going to look at an example of that. That's this last problem. List the following substance in increasing melting points. Okay, so it's increasing. So let's do this one first. And I'm just going to put a little division point right here. So I'm going to have all this room to do A, and I'm going to have all this room to do B. Okay, so first I need to figure out what is the difference in these. Well, helium is going to, what kind of intermolecular force is that going to have? Well, that's only going to be these London dispersion forces. Helium isn't bonded to anything else. It doesn't have any polarity on its own, so helium is going to be really weak. So it's going to be at the lowest end. After that, well, what else do I have? H2O. What kind of bonding is that going to do? Think about it. Well, that's going to participate in hydrogen bonding. Okay. What about diamond? Carbon as a diamond? Well, diamond, like I said in the video, did I say that in the video? Well, you should have seen it in Crash Course. Diamond is a network covalent solid. So all these carbons, they're just connected to other carbons. There's no division point. There's no clear point where this molecule ends. The entire diamond, like if this pen were made of diamond, it would just be bonds of carbon all the way through. It wouldn't be these individual molecules. The whole thing would be one giant molecule, which is what makes that very strong. So diamond, that's really going to have our highest melting point. And if you weren't sure, you could look that up. That would be a thing to Google just to make sure, especially when we're looking at the difference between a network covalent, an ionic, and another ionic. That's really going to be a big, they can really be very close in their melting points. So then H2O, clearly that hydrogen bonding, that's going to be lower than both our network covalent and our ionic. So H2O is going to go next. And what comes after that? Well, it's either going to be the diamond or it's going to be one of the ionic substances. Now, looking up the melting point for diamond, it's about 5,000 degrees. It's got one of the highest melting points of any substance. So that's not going to go next. We're going to have our ionic substances go next. Now, what's the difference in these two? Well, the ionic radius is not that different here. It really isn't. But what is different is our charge. So calcium chloride has a bigger charge than sodium chloride, so that is going to be more attracted, right? It's going to have that stronger force holding it together. So it's going to have a higher melting point. So next is NaCl. After that is going to be CaCl. And then after that is going to be our diamond. There we go. And that's how we answer that one. All right, now B. We've got aluminum phosphide. Now, what are the charges on aluminum phosphide? If we look at our periodic table, aluminum's a +3, phosphide is a -3, okay? Now, oxygen, so obviously aluminum phosphide, that's an ionic compound, we should know that. Oxygen, what is oxygen? O2. Is there any polarity there? Well, if I take the oxygen, I go O, double bonded to O, that's all that's going to look like. Well, it's the same molecule, so there's no electronegativity difference, there's no polarity there. So the only thing holding oxygen together is going to be London dispersion forces. Okay, so that's going to be really weak. HF, hydrogen fluoride. Well, this would really be hydrofluoric acid. Okay, well, hydrogen to fluorine, that's going to be a covalent bond. Okay, but that's one of our 3 hydrogen bonds. Okay, all right, that makes sense. H2S, H2S. Well, now this is a covalent bond. So H2S, that's really going to be, that's just going to have a polar bond. So that's going to be polar. This is going to have a hydrogen bond. Hydrogen bonds are better than polar bonds. And then MgO. Well, magnesium, what's the charge on magnesium? It's going to be 2+. Oxygen, that's also going to be a 2. All right. Well, obviously, our oxygen is going to have the lowest melting point. I mean, think about it. This oxygen, we breathe it in. It's a gas at room temperature. The rest of these are all, well, these two are liquids at room temperature. These two are solids at room temperature. So oxygen, having London dispersion forces being the only thing keeping them together, that's going to have a very low melting point. After that, we're going to look at our covalent substances, because those are always going to have a lower melting point than our ionic substances. And then to differentiate the two, well, this one's polar, this one's got hydrogen bonding. The polar one is going to be weaker, so it's going to have a lower melting point, so H2S. And then next, we're going to have hydrogen fluoride, hydrofluoric acid. That's with that hydrogen bonding. Finally, we're going to have our 2 ionic substances. Now, what's going to be the difference in these? Well, our ionic radiuses, if we look at these, magnesium and aluminum, they're right next to each other on the periodic table. Oxygen and phosphorus, those are really close as well. They're really only 1 row apart. So the difference is really going to come down to these charges. So then the lower charge is going to have a lower melting point. So MgO is going to be next. And then aluminum phosphide, that's going to be last. It's going to have our highest melting point. And there we go. Hopefully that makes sense. If you have any other questions, let me know.